Good evening and once again welcome back. We are into the final session of the 6-day FDP Next Gen AI training. And the concluding session is about building tomorrow with large language models, intelligent agents, and beyond. We know that intelligent agents are everywhere and they are aiding us in every activity nowadays. To give us a presentation and share his knowledge on the topic, we have the resource person, Ebey Abraham. He's a senior researcher in Microsoft Applied Sciences Group. To introduce him and to invite him into this faculty development program, let me invite our respected HOD, Dr. Unnikrishnan. Thank you.
Thank you, sir. Ebey is a senior researcher in the Applied Sciences Group at Microsoft, United Kingdom. Currently, he works on large language models with a focus on productizing them to run on edge devices. Prior to that, Ebey worked on computer vision models for Microsoft Surface laptops. Ebey completed his MSc in Computer Graphics Vision and Imaging from University College, London. Prior to that, he worked as a research software engineer at Nissan, working on automated analysis of cars and smart assistants for improving in-car user experience. This is the formal introduction, and above all that, he is very close to our heart, right? Heart of RIT CSC department. He is one of our alumni, and wholeheartedly we welcome you as a resource person of this program. Thank you very much, Ebey, for accepting our invitation. Very happy to see you. Thank you. Thank you.
Thank you for the introduction, sir, and Shilkumar, sir. So today, I will be giving a short presentation on agents. I hope my screen is visible. Today I will be giving a short presentation on building tomorrow with large language models. The basic introduction is that I'll start with a brief overview of large language models, what the foundations and architecture are. Then we'll cover LLMs as intelligent agents, so how the basic interactions from LLMs can be composed into like solving complex problems. Then we can go into the engineering solutions which have improved the performance of LLMs and their applications as agents. And finally, we can talk about the future of where these agent frameworks are going and how they are transforming our current work style. Okay. Okay. So this here shows a diagram of what the basic component of large language model looks like. So this is the foundation block for all large language models which exist today, including GPT-4, Llama, any language model you take. The basic component is this block, which was introduced in this paper called "Attention is All You Need" by Vaswani and group from Google. And one of the key components which they introduced was this multi-head attention block. So what this does is it computes so when you give it an input text to the LLM, it needs a way to compute the relationship between the different tokens. So it needs to compute like which part of the input text is related to which other part coming in the past. So this helps basically build a relationship and like between the tokens and like help understand what the input text is actually meaning. And the second important component is this positional encoding. So in addition to computing the relationship between parts of the text, we also need to know the order in which the input tokens are fed to the model. So to incorporate that, we have this component called the position encoding, which is basically a sine wave or a cos wave, which acts as a function of x, and you add that to the input embedding. So as your position increases, that position encoding is added to the input embedding to make sure that that information is also added when you're processing the embeddings downstream. So these two components like played a huge role in the advancement of LLMs, and from this paper, "Attention is All You Need," it was like their basic contribution was that you only need these two components, though, which are the major contributions to understanding text, rather than the encoding or the decoding of the user text. So with this basic structure, the foundation of all model LLMs was started. So anything which involves translation or text completion, this is the basic structure which is followed. So in addition to structure architecture, what else do we need? So other than that, the other major component is collecting training data. So once we have the architecture or the model defined, we need to identify like what data we need. We need to train the model. So initial approaches was just to crawl the internet and get any kind of data which is required. So initially, platforms like Stack Overflow, Reddit, and all this internet sources were crawled, and data from these sources were used as is to train the initial version. So this was what GPT 2, 3, and 4 were initially trained on. But the issue with these raw internet sources is that there is too much noise in the data because there is no like constraint on what the internet users are typing. So it might contain a lot of noise in terms of random characters or the text in other languages and so on. So one of the major contributions which Microsoft Research did was introduced in this paper called "Textbooks Are All You Need." So what this team from Microsoft introduced is that you don't need to have very large amounts of data to train an LLM. What you need is big enough data, but as long as the data is clean, it will give you the same performance as any bigger model. So here you can see the an evaluation percentage of different models of different sizes. And you can see that this model, which is called 5 from Microsoft, even if it's only a 7 billion parameter model, it performs in par with like a 1 trillion parameter model or a 52 billion parameter model. It even surpasses these models only because the data which they use for training is much more cleaner. So this is now an ongoing work stream in how we can collect like good quality data rather than huge amounts of data. So with this basic finding, we at Microsoft have worked on like a family of models right now called the 5 family of models, and the idea is still the same. You generate data based on synthetic approaches rather than uh, internet crawling to make sure that the data you generate is clean and efficient and not just, so basically the summary is that quality over quantity. So this is another example from the work we did. It was so this shows the improvement in the benchmark with with the data sets. So the orange bar is the performance on the Stack Overflow data, which is crawling the Stack Overflow database and generating the question and answers. You can see that just training on the Stack Overflow data, you only get 11-12%. But with the synthetic data, you start getting much more higher evaluation accuracy compared to the just using internet scrolling data. For some context, the code textbook and code exercises, this is synthetic data generating using GPT-4. So what the team here did is they used GPT-4 to generate a textbook for Python coding. So instead of crawling Stack Overflow and getting Python question and answers, they asked GPT-4, can you generate like a textbook from scratch for programming? And they used that for training instead of the Stack Overflow data. So what that meant is that the data which they were using was in a much cleaner format without and in a much structured format. So this is like a really important factor when it comes to training large language models. And yeah, finally, the last component is obviously the compute, which like for training any large language model, you need like, because there are so many parameters which you need to optimize, you need like large amounts of GPU. And this is the reason why it is mostly the large companies which are often generating these large language models and not, it's not coming from academia as such. So here, like the more resources you have, the more chances you have in like pushing forward the limits of large language models. So because this is a problem that you need like large amounts of compute to train large language models, the research in academia is trying to come forward with methods which try to reduce the amount of compute required. So what if I only have a small amount of GPUs and I still want to train LLMs? What can I do? So there are some methods which are currently in research to like reduce the effective compute cost in LLMs. So one of these methods, I'll just talk about one of these methods, which is like low rank adaptation of weight matrices. So traditionally, like the normal way of training a network is that you have this weight matrix, which you need to update in each training loop. So this W weight gets updated as W plus delta W. Delta W is computed with each training sample. So instead of that, what these authors suggested is that you decompose this delta W into like two smaller matrices, B, A, and B. So the rank of the matrices will be like much less than the dimension of the weight matrix. So in effective, while you have the same dimension, as the delta W, your rank of the matrix will be much small. So you need to train very few parameters compared to the actual model. So using this approach, you can fit like large models in like desktop GPUs, and you can fine tune them for other tasks. Obviously, this comes with the limitations, but at least this enables users which don't have access to like large compute resources to train their own models. And this method is efficient enough that a lot of the current research which is going on in large language model development is evolved around adaptation methods rather than training models from scratch, because this makes more sense. If you propose an idea and it works with low rank adaptation, then you can extrapolate that and say, okay, if this works with low rank adaptation, it can work with training the usual way. So that was a basic introduction to LLMs. Now we can move on to the other application of LLMs, basic as agents. So till now, LLMs have been used as text completion. You can ask it questions, it can generate answers for you, or it can translate text. Or if you want information about something, it can generate answer for you based on that. But what if we want to use LLMs as agents? Basically, give them a task and let them use all tools which humans would use and complete the task for you. Is that possible? And uh, what status are we there in terms of that? That's what we're going to look in this section. So one of the key requirements for LLMs to be used as agents is like, the reason why we want to do that is because we want to give LLMs autonomy in terms of tasks, which is like we don't want human feedback every time in between. For example, if you want to do a process an Excel sheet, we don't want to tell the LLM, okay, look at these columns in the Excel sheet and then apply this formula and then look at this graph and then uh, process the data. Instead, we just give a task to the LLM. The LLM needs to figure out what to do on its own without any human feedback. So that's one requirement. The other is advanced reasoning and planning. So like in the same Excel sheet example, the LLM needs to be able to recognize that this involves a lot of steps, and at each step I need to verify what I'm doing is right or wrong. And the third component is the interaction with external tools. So when you give autonomy to an LLM, you also need to give it access to other tools. For example, uh, if it wants to do a mathematical calculation, instead of relying on its own knowledge, it can use a calculator API instead. So that will give it a more reliable answer than just using its own knowledge. So here, like giving LLMs access to like external tools, this can be existing APIs or web APIs, anything which the LLM can use on top of what it already knows, that will be really helpful in like agentic frameworks. So a basic structure of an agentic framework looks like this. So you have agent core in the middle. So this is responsible for all your interactions. So given a user request, it goes to this agent core. Agent core has access to roughly 3 components. So this is a very simple diagram of what an agentic framework looks like. So it basically has an access to a memory module. So this will be responsible for holding anything which the agent can refer to at a later stage. Then the planning module. The planning module is responsible for decomposing uh, decomposing user queries into like simpler steps if the user is requesting something really complex. And the third component is the tool component, which is like I mentioned, access to external APIs or something like that. So we'll just go through each of these components one by one. So the agent core is responsible for the core function of the agent, like I mentioned. So if all interactions from the user, it will go to this agent core, and the agent core is responsible for orchestrating between the different components and making decisions based on the inputs from the different components. So if the user types in something like, okay, I want to generate uh, like generate a forecast of my next financial year, the agentic core needs to look at the available tools and look at the files of the user and find the file and do all that. So the agentic core will be responsible for that. It also is responsible for like identifying what tools are required for performing a given task. So if the user types in a task, the agent core should identify, okay, I need these APIs or these tools to solve the user task. And based on this, it will also generate a plan for the input task. So what this does is, suppose you given a really complicated query, the agentic core will use the planning module and decompose into like multiple steps, and then solve each uh, independent task on its own, and then use the output from the previous task as the input, so on, solving a very complicated task. In addition to all this, it is also responsible for maintaining the uh, memory or persona. So, for example, if you are interacting with an agent, you would want it to uh, recognize you as a user compared to other users. For example, when you're listening to music on Spotify, it will often adjust the music suggestions to your music taste. So, like that, uh, ideally, an agent should be able to recognize that what you as a user prefer compared to a normal user. For example, if you ask it to like edit your photos, it should have some understanding of how you like your photos. So uh, all this responsibility comes on the agent core. It tries to understand like what you as a user prefer, and then stores it in the memory module. And then next time when you ask a similar question, it retrieves it from the memory module and then uses that as a reference for completing your task. Uh, and a bit more detail about the memory module. So like I explained, it basically stores any relevant context which the agent can use for solving tasks. So this can be like internal logs or some conversation which has happened between you and the agent. It can also be preferences like your name, your preferred method of sending email, or your preferred set of applications. So this can be roughly divided into short-term memory and long-term memory. For example, if you ask it something like uh, your name or your set of applications, that will be stored in a long-term memory because that will often be used in a lot of different contexts. But for much simpler tasks, it will just use a short-term memory just to keep uh, track of its internal state and use that for a task, and then uh, replace that when the task is over. Uh, the memory module can also be used for like retrieval methods. For example, uh, it can be a database which you give access to the agent. So suppose you give it an, access to documentation of an application. So when you ask the agent to do something, it can refer to the documentation and then make decisions based on what it has read in the documentation. So this way, you are not like the agent has access to one more resource it can refer to, and it can verify whether its understanding is correct. So this way, like if you like providing database helps in, or providing external knowledge bases helps in verifying the knowledge of the agent itself. Um, the other component in the agent framework was the tools, which we had talked about. So, like I mentioned, the tools can be any third-party APIs. So, existing APIs which are already being used, these can be exposed to the agent framework, and the framework can reuse these APIs to solve user tasks. For example, if an API for getting the weather exists, and someone asks the agent, "Can you recommend what whether I should take the umbrella today or not?" the agent can just reuse the weather API instead of writing its own code and then writing its own API to get the weather. It can just reuse this weather API to get a response to the user. The other kind of tools are also like code interpreters. So, for example, if in the first case, if the agent does not have access to its access to a third-party API, for example, if the user asks to draw a plot with the given data and the agent does not have access to an existing tool which can draw a plot, what it can do is write a script on its own, which can uh, be run in a sandboxed interpreter, and then it can generate the plot based on the code it generates. So instead of relying on a third-party API, the agent just writes its own API, and this can be cached later on and then used as an API by the agent in future scenarios. And the last component which comes in the agent framework is the planning module, and this is like one of the most complicated components to implement. So if you look at the planning module, it can be roughly decomposed into two steps. One is task decomposition. So here, the planning module, what it does is it is responsible for breaking down a complex user task into like smaller, simpler steps. For example, if I ask it to get the forecast for the financial forecast for the next year, it needs to solve many individual steps to get to that final stage. So here the planning module is responsible for decomposing it into like simpler steps which can be solved and then accumulating all that knowledge to get a response to the user. And the second component is the reflection and critique. So because this complex task is decomposed into smaller steps, at each step you should be able to verify that have I done correctly in the previous steps, similar to how a human would solve a complex step. At each step you would look, have I made the correct decision here, and going back it will look at the previous output and verify that it has done the correct step. So this reflection and critique step needs to be there in the planning module so that it makes the right decision. Um, yeah, coming to the task decomposition. So yeah, so this is the just some example of how task decomposition looks like. For example, if you ask the agent like what are the key takeaways of the FTP session, it might need answers to the following like simpler queries like what was the FTP session about, like did it have talks on like latest trends, what are the relevance of the talks to the job market, and based on like answers to these questions it can like generate a response to the original question, which is like what are the key takeaways from the FTP session. um, and for reflection and critique, I just wanted to go a bit more deep into this because there is a lot of ongoing work on this. So this is a very engineering solution based. So one of the very uh, key components in this is prompt engineering. Like how are you structuring the prompts to the LLM? And the simplest way is zero-shoot prompting. So this is how we usually interact with LLMs. So you type in some text to the LLM and it generates the output. For example, here I'm asking it to classify the text into neutral, negative, or positive. And the input I give it is, I think the vacation is okay. So here the model will output, okay, the tone of the text is neutral. But what if we want to give the LLM some examples of what it needs to do, and based on that, it generates some output? So here we have this prompt engineering method called few shot prompting. So what it looks like is I give it some examples on what it needs to do. For example, this is awesome is a positive example. This is bad is a negative example. Wow, that movie was good is a positive example. And then I finally give it a new query and ask it to like classify it based on the examples I've given. So where few shot prompting helps is that when the model has no knowledge about what is going on, providing examples pushes it towards giving correct answers based on like the examples you have given. So this is helpful in like uh, tasks which the base model is not proficient in. For example, if you wanted to solve like complex mathematics, then you can give it some examples on like how to solve some questions, and based on that knowledge, the LLM can like solve like further questions. Yeah. Now, after few shot prompting, even one of the drawbacks for few shot prompting is that it does not work with very complicated tasks. For example, here I've given it an input. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. So this is one example I've given to the model. Then I asked it another question. The cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? And the output that the model generates is the answer is 27, which is incorrect. So instead of this standard prompting, you can do chain of thought prompting, where uh, you write down the thinking process behind the problem solution. So here, instead of just writing the answer is 11, I can show the LLM how I am computing the answer. So the Roger, I can tell it that Roger started with 5 balls, then he got 2 cans of 3 tennis balls, each is 6 tennis balls. So in total, he will have 5 plus 6 equals to 11. So providing this context and then asking it the same question again, you can see that the model is following the same format. It is like thinking out loud, basically. It is, and this way it is able to generate the right answer, which is 9. So this chain of thought prompting was introduced in this paper linked here. So what they showed is compared to standard prompting, if you use chain of thought prompting, you get much better results because the model is forced to think out loud, and that way the generated answers are much more sensible when it comes to the problem, rather than just generating answers on the training data. Another component of so chain of thought prompting is uh, one of the like leading methods which are used in prompt engineering, but we also have much more complicated prompting frameworks which are used for like agentic tasks. So one of the example is this React framework. So here it builds upon the solution explained in chain of thought prompting. So instead of just giving it one chance to think out the solution, it goes through a loop of reasoning and acting. So here I have given it an example, like this is the question I've given it. Aside from the Apple remote, what other devices can control the uh, Apple program, control the program Apple remote was originally designed to interact with? So this is like a complicated problem. Basically, you want to find what other programs can the remote control. So here the agent first, like the LLM first generates a thought, like I need to search Apple remote and find the program it was initially designed to interact with. And it finds some data, then it goes through the second loop of finding that relevant information, and then goes to third loop and fourth loop. It finally finds out the information that in addition to the remote, you can also use the keyboard function keys to interact with the software. So this is more in line with how a human would solve a task. Like you go through multiple reasoning and acting solutions. Like you go through the search space, and until you get to an end, you exhaust that, and then maybe you go back again, and then go down a different line and then find the solution. So many more prompting frameworks like this exist, and each have their own pros and cons. So depending on the agent framework that you want to implement, you might have a different prompt engineering method that is implemented in the framework. Okay, now we can talk about the engineering advancements that have helped in like advancing being able to push agents to like production level quality. So up till this point, we have talked more about like research standpoints, and but to actually get it to a product stage, we actually need like engineering solutions to these problems. So like this image shows that research alone cannot get you to a product. You also need engineering. So the major question is like, you have all these existing tools which are available to the user. For example, on a mobile phone, you have already so many applications which the user is using. How can you tie these applications to an LLM so that it can do an agentic workflow over these apps? The major problem here is that there is no like standard API definition for these AI workflows. Like how there is no standard definition on how these applications can interact with LLMs and how the LLM can access data from these applications. So here, like in the last year, this company called Anthropic introduced Model Context Protocol, which standardizes how applications provide context to LLMs. And Google has introduced agent-to-agent protocol, which standardizes like how different agents can communicate with each other. So these two protocols are like one of the building blocks now on how agentic frameworks are built. I can talk a bit in detail about these two. So coming to model context protocol, the problem this tries to solve is you have an agent which has all these components tied together, and you have all these applications on a user device. And now, how do you enable like communication between these two? For example, I might ask the agent to like send my playlist to as a mail to my friend. So here the agent should be able to access my songs and then send it as a mail through Outlook. So how does this interaction happen? So for this, the solution which Anthropic came up with is to define a context, a communication protocol between an AI application and an API. So the basic component is this: each AI application will have, so your framework will have clients which will have a one-to-one connection with an MCP server. So the server can be an application or a bunch of APIs, or it can be also your file system or your database. So once this one-to-one communication is established, if the AI application requires any data, or access to tools, it goes through this client-server communication protocol to get access to this data. And how this helps is that the um, implementation of the API on the server side does not affect the how the data is transferred between these two. So the implementation of the API can be any way, but between the client and the server, the data transformation happens, which like enables us to reuse any existing API as long as they are exposed through this MCP server. Uh, Similarly, we have this agent-to-agent protocol also, which is now you have this agents which have access to APIs and through the MCP server, and there is another agent which focuses on some other task, and it has access to its own set of APIs or applications. Now, what if this agent needs access to some tools which only this agent has access to? So here we have the need of an agent-to-agent communication protocol. And this was introduced by Google recently, where they define a framework. This is also in theory similar to the MCP protocol. It's just a JSON RPC structure happening over HTTPS. And when the agent needs any information which the other agent has, it just sends over a request and gets back the response. And this way it enables like agent-to-agent framework, agent-to-agent communication. In addition to this, this protocol also adds agent cards. So when you have like multiple agents working together, you need some way to define what each agent is doing. So this agent card defines basically standardizes how the agent capabilities are defined. So for each agent, you'll have an agent card which will list out what the agent is capable of, what it can solve, and what tools it has access to. And if uh, if an agent requires some capability which it does not have, but some other agent has, it can communicate with that agent through this protocol and get access to those capabilities. In addition to this, it also allows for like transferring multimodal data between each other. For example, if you have an agent that only works with text and you have an agent that works with images, and you need to do something which involves both text and images, you can have a collaboration between those two agents to solve the common task which involves like both modalities. So now that we have a basic understanding of what the different components of an agentic framework looks like and how these are all tied up with the different engineering solutions which are currently existing, we can talk a bit about like what the future of intelligent agents looks like and how they are transforming our current work and education system. So personally, from a long-term thought, what I think is that the agents are slowly becoming more and more sophisticated, especially now that we have a way to interact with existing tools and existing applications. So what this means is that suddenly our agents have access to so much information sources and so many extra capabilities that it can solve much more complex tasks than it was initially capable of. So now that the agent can collaborate between multiple agents and it can collaborate between multiple applications, it has that sense of autonomy, which initially it was not there because you needed to add it to the training data and all. But because of these communication protocols which have come up, and because now these can be easily exposed, it really increases the sophistication of the agents. And the ability of agents to communicate with each other, that also enables a lot of complicated problem solving, because you can have multiple different agents which are specialized in their own field. So this is very similar to how our engineering fields are distributed. You can have an agent specialized in computer science engineering. You can have an agent specialized in civil architecture and maybe mechanical and all those fields. And to solve a very complicated engineering task, you can have these specialized agents come together, communicate with each other, and collaborate using their own domain expertise, but sharing their knowledge to solve a common task. And I'll just conclude by sharing this example of one of the agent frameworks we have developed at Microsoft, which is currently being shipped at with the Copilot, Microsoft 365 Copilot. Let me show you.
Hi, I'm Ashok, and I'm here today to show you our new analyst agent in Copilot. We built analysts to think like a skilled data scientist, so you can go from raw data to insights in minutes. Analyst leverages a state-of-the-art reasoning model that we've optimized for advanced data analysis at work. It's based on OpenAI's O3 Mini. Now, let's see the agent in action. Imagine I'm in marketing. I'm trying to understand our most loyal customers. I have this really messy data set. You can see thousands of rows and a few tabs across customers and their monthly revenue, and none of it has been cleaned or contextualized. Usually, to make sense of this data, I'd need to ask my colleague who knows Python. But let's try the analyst agent. I don't have to spend time writing the perfect prompt to get what I'm looking for. I'll just ask it to help me come up with an easy way to learn and visualize my customer base. You'll see the agent takes my question, understands the task, and constructs a plan to reach an answer.
So just to highlight, like, this is the planning component. So it takes in the query you typed in, and it decomposes into like smaller tasks which can be solved.
It also identifies the Python tools it may need to complete the task, just as a data analyst would. It can take any complex data set, make sense of it, and execute Python code to reason through the questions you have about the data. If I want to see more into its thought process, I can always click and see its chain of thought reasoning, as well as the Python code it's running in real time. This allows me to validate and trust in its thinking and approach. Analyst is already on to the final step and starts working on a visualization. Now I've got the answer I was looking for. With Analyst, now every employee has access to their own 24/7 data analyst. It knows Python, it's right within Copilot, and it uses chain of thought reasoning so you can check its work.
So I'll just highlight a few components here. So you can see that it has access to the Excel sheet initially.
You'll see the agent takes my question.
So that it can read, and then in some scenarios it does not have access to the tools, so it writes its own Python code to generate to solve the task. So this is where like interaction between multiple tools is relevant for like complex problem solving.
And understand.
I'll just conclude by saying that this current developments in like agentic frameworks have like a vast potential, especially when coming to like current work methodologies, especially like a lot of repetitive tasks can be assigned to agent frameworks, which can be which they can handle on their own. This can be especially seen like in coding scenarios where like you have to maintain a large database which doesn't need like too many updates. Then you can just assign an agent to it for like sequential updates every now and then based on its understanding. So you don't need a user, a human in the loop to maintain a like a large code base, and you just assign an agent to do this based on its understanding. So personally, I see that a lot of repetitive tasks, which usually humans used to do, would most probably be replaced by these kind of agentic frameworks. Hopefully, that helps us to work more into like new kind of paradigms in engineering and technology, and yeah. Any questions?
Questions from participants? I have a question, Ebey. Normally, the LLM models are actually failing whenever they are giving the code with the old libraries. And then, in that scenario, they have to debug to include a new library. So, in that case, how it will behave? What are the possible solutions?
Yes, so that is where this tool calling comes in, becomes helpful. For example, if I show this, the traditionally what happens is, for example, you ask maybe GPT-4 to write a code using like very old libraries. It is possible that the training data does not have enough examples based on which it can generate code on its own. But with this kind of architecture where you have access to a memory module, you can ask the agent to refer. For example, if you want to make it write code in Visual Basic or some old programming language, then you can just give it documentation on that along with a bunch of examples, and then it can refer to this documentation and then write code based on that, rather than relying on its own training data. So this is where the like framework comes in handy. Instead of working on its own, you have access to all these different tools which can be used as input to like generate plans. Like similar to how we as students, when we need extra knowledge, we often go to the library and refer to books. This is kind of like that. I hope that answers the question.
Okay. Any questions from participants?
So any more questions from the side of the participants? Yeah. Otherwise, it was a fantastic session, maybe, and we got introduced into the LLM agents. This is actually so. This is in. So again, sorry, there was some network issue at our side. So this was a fabulous presentation. We got introduced into the concept of LLM agents. We all know that we have been using LLM agents for various purposes, and you had a magnificent explanation of LLM agents and their concepts. And from the side of Department of Computer Science and Engineering at Rajiv Gandhi Institute of Technology, I would like to extend our sincere thanks to Ebey, and we value you the most. And we would like to have you as resource persons in our future sessions also. And once again, thank you, Ebey.
Thank you so much for this opportunity.
Thank Thank you very much, Ebey, for coming as a resource person for our faculty development program. We are really happy and proud to see your growth from a dedicated, hardworking, sincere student to a professional. Hope you will reach more heights of success in the years to come. Thank you very much.
Thank you so much.